I'm going to try and fit the whole of the pipeline of metabolomics into 40 minutes, and I will endeavour to give a few ideas of how to keep forward. Yeah, I basically started NMR Metabolomics in Liverpool in 2013. Since then, we've got a lot of experts from all over who actually joined us in Liverpool. I'm just going to see if I can get my pointer up. Excellent. Okay. So I thought I would give myself a challenge for you all this afternoon, keep you all awake. I'll start by talking briefly about the metabolomics pipeline. We've got some experts assembled here to tell you more details on some aspects of the pipeline and some common approaches to NMR metabolomics. So it's my delight to talk to an NMR audience because it's usually a lot of MS people who are interested in metabolomics, and NMR is an afterthought potentially. That might just be my experience, but actually I believe and I've experienced that NMR has a lot to offer. So actually being able to talk to you about how we should exploit it and how we should get the most out of metabolomics as an NMR community is really what I'm here to bang the drum for. I also have a particular enthusiasm for lipids in NMR. That's something that I think we can offer a lot more than we currently do to the metabolomics community. So I'm going to cover a few on databases and resources. Work with Phelan to actually try and get CCPN and Morgan at the back there to do metabolomics has been really successful, and we want to build on that. And so then I will talk about future directions. And I'll run out of time, but there are case studies at the end that you can go back on the recording and pause probably. So let's start with the metabolomics pipeline. So there's a lot to cover. Study design, sample collection and sample preparation are the ones that I think get the least considerations upfront, and that is the death of any metabolomics project in particular. I think that's probably true for all disciplines that are going to talk this week, but more so for metabolomics. And then I'll talk more on the NMR side of things, because as I say, it's nice to have an NMR audience to talk about metabolomics. And then the challenges in open access data, common statistics, pathway analysis, I think is a talk for another day. And there's statistical analysis that's going to be covered by my colleagues here as well. So yeah, so when you're talking about metabolomics pipeline, you want to get like a simple bog standard SOP, and you want to get going, especially if you're the NMR expert and people come to you with a study, they just want to know how to do it and how to get going. Well, it really does depend on what your samples are, how you want to actually approach it, and what the biological question is as well. But really, if you can crush it down and solubilize it, if you can get it into a rotor, or if you can get a fluid out of a biological organism, then you're good to go. Everything has metabolites in it, but it's how to make sure that it's actually of value, the research you're doing. So really what we think about in the metabolomics pipeline is data is biological meaning plus error. And this is where you really have to think about controlling for all of the things that will completely scupper your metabolomics pipeline. And that's in sampling and measurement, environmental variability, as well as mistakes that can happen either in labeling samples or approaching patients, or even diagnosing people to the right clinical group. Obviously, you can't control natural variability and shocks, and this one looks like a quite small version of the proportion of the plot, but given that biological processes in humans are extremely complicated, and we do our best to challenge it even further by our vices and our different lifestyles, that is something that you really need to ensure that you have a large enough sample to account for all the variability that you'll expect in your sample. So I think all of us here this afternoon will tell you about the 3 R's of sort of making sure you have a good study design, which is to reference everything properly, to replicate, provide enough replicates to overcome the natural variability within your study, and that will depend on the study you're looking at. And also randomize, okay? You can't do all of your plants in one greenhouse with one particular knockdown and another greenhouse with another knockdown. You can't even use your scientific method to actually put all plant A in a row, plant B in another row, because the sun's going to come in at a different angle. And that's just plants. Okay, so when you start to talk about humans, you can't collect all your study from one patient hospital and then have the other patient cohort from another hospital. It's just not going to work. So randomization happens even before you get anywhere near the spectrometer. So I've got a couple of examples here of what you might need to think about. Again, these are broad generalizations. We've done a lot of studies here. I'm going to throw a lot of little references along the bottom of the slide. Some of these are PhD thesis that have actually come out of Liverpool. Some of these are seminal works from the field. And if anybody wants literature, I have it in spades. I'm happy to share all the OIs with you afterwards. There's way more than we can cover in an afternoon. Basically for the clinical studies among you, it's really a fasting blood draw that you want. And you even want to think about dietary restrictions. And these are things that are really challenging to control, especially in a general population. And you have to make sure that all sites in your study adhere to the same SOP. These are serum samples collected at hospitals, so hospitalized patients. So all these patients actually were in hospital for the same condition. And each of the colours and shapes represents a different hospital. Each of the dots represents the most variance between samples. So each dot represents a sample, and we'll explain what we mean by these PCA plots before. So that is what this is. What you can see is that we have maybe 7 or 8 hospitals and variance that is not due to the disease condition. Okay, so these are things that you need to actually engage with the clinicians before you even start to think about doing a successful metabolomics study. The other thing is about how much variance you're going to have, how much noise is going to be in your data. Really depends on the sample size and the method you're using and the equipment you have to drive that method. So as you go down in the grams of tissue, the actual noise in the data becomes completely unworkable. So you really need to think about what works for your study. So then when you've got through the first challenge, you need to make sure that you know how to handle your fluid or your material, if it's a cell or a tissue or a plant. You actually need to make sure that you can get it into an NMR tube. Mostly we do NMR in the solution state, and that's really where I'm going to focus today. If it's a proteinous fluid like blood serum or blood plasma, then we really want to dilute that down to make sure it's as narrow land shape as we can for NMR. You also want to think about actually adding a lot more buffering agent if you're using something with a high ionic strength like urine or media. And then if you're in the extracting of metabolites from tissue or cells, then you can go ahead and use a pure deuterated buffer, which obviously is a lot cleaner. You need to think about blood collection tubes, especially for EDTA-free, glucose and citrate, additives, coatings, gel membranes, all these things cause problems with your metabolomics collection. And I would say that it's best to talk to the clinicians before they just grab what they usually use from the cart in the corner. Every single brand has a slightly different NMR signature, and unlike chromatography, where LCMS, liquid chromatography, or GCMS, gas chromatography, are actually separating out these metabolites from each other, and they can somehow get away with some of these additives. Everything in the NMR tube is in together. We're not tending to do LC NMR, although I'd be interested in those who are interested in testing that out. So the metabolomics pipeline, as I see it, is basically we have a biological sample, and we take that as a fluid and we spike it, or we resuspend an extract, or potentially we might extract in a solvent from the fluid, and then we pop them straight into NMR tubes, or we'll actually go through some sonication or other homogenization of the material before freeze drying to actually getting them into the NMR tube. And then we use an autosampler such as a sample jet, which keeps things in a controlled, homogeneous environment ahead of going into the NMR spectrometer. So when you're thinking about data acquisition, the things you need to think about are per batch and per sample. So run blanks, run pooled samples as well, run temperature calibration, make sure that the temperature that your samples are experiencing inside the probe is exactly as the temperature reading on the actual the display of your spectrometer software. Typically TopSpin is telling you. So we use a deuterated thermometer that works really well for the range of temperatures that you find for biofluids. We run viscous materials at 310 Kelvin or 37 degrees Celsius. We run less viscous materials at 25 degrees Celsius or 298. And if you've got volatile materials such as chloroform, we tend to run at 15 degrees Celsius, 288. But again, these are not really standardized yet in the methods, and that's something that we're trying to work on. So we also do a 3D shimming routine every batch. The protein people love it when they come to my spectrometer because it's really nicely shimmed. Basically, we keep it nice and tidy, and we check that with the sucrose standard that we get from our NMR vendor Brooker, and we make sure that our line width falls within the accepted tolerance for the day that the spectrometer was installed. So that's your quality assurance. That will also make you very popular with pharmaceutical companies as well. So if you can make sure that your spectrometer is set up the same every time, any variance that's happening within your NMR tubes is down to the NMR sample. And that's really, really mission critical. I should give a shout out to Pete Gareth, who actually set up our facility for metabolomics back in 2013, because he came with all these stringent rules that we have applied and used ever since. And then when we're actually in the business of running the samples, we run them through an automated spectrometer interface that some of you may not have had the pleasure of, Icon NMR in Brooker. This is a little bit of a configuration nightmare, but once you've got that set up, what you want it to do so that you can go home and not have to run through the serum samples over the weekend is to transfer your sample, calibrate the temperature, as in equilibrate the temperature, that should really say, and automatically tune and match your sample, lock, shim, phase optimization, pulse calibration, and then a standard suite of NOSI GPPR1D plus processing, a CPMG plus processing, a diffusion filter, and a JRES. And that shouldn't take you more than an hour per sample. You might want to drop one or two of those depending on the sample type that you're running, but more on the pulse sequences later. Once we've got the samples off the spectrometer, then obviously the key activity is to make sure that they pass the quality control. If they do not pass quality control, you might get away with running them again. You can check against your code QC to make sure that they are not degrading over time. It does depend on the type of fluid or extract that you're using, whether you can get away with this. Because the metabolome is metabolites are breakdown products, and things will continue to break down. Okay, so although your NMR sample hasn't gone anywhere, even the protein people know that your protein isn't good forever, right? So you've got to be very, very time sensitive with what you're doing with metabolomics, and make sure that you check that at the end of your run. But broadly speaking, there's a lot of protocols here in best practice. There's the Metabolomics Standards Initiative, or the MSI, who've written a load of documentation. And recently, the delightfully acronymed MQAC, which is the Metabolites Quality Assurance and Control Consortia, have taken up the mantle of publishing guidance on how to do things effectively. So when we're talking about NMR, which isn't talked about a lot, I would say, in the MSI, is referencing baseline signal to noise, water suppression, and phase. So make sure that you see what you expect to see. Now, signal to noise is a bit of a knotty issue. If you're using urine, then you're going to have a range of signal to noise because it's just basically how dilute the urine sample is. However, if you're extracting cells of a given value or a tissue of a given mass, which you really should be doing, you should expect a much smaller range of signal to noise. So these are the important things that need to go into that pipeline before you can even start to do any analysis on your data. So this is normally where I start to talk to people about metabolomics, because I'm more interested in what happens afterwards. I mean, I think we can spend a little bit more time on what happens in this one-dimensional NMR spectrum, because really we want to get the most information out of the NMR before we go to this matrix of numbers that actually is interpreted by a wide range of software and a wide range of analysts. We're really interested in how to get from typically one-dimensional NMR, although Christian's going to talk about the other options, and actually get from a spectrum to a matrix of numbers with information on what metabolites they correspond to. So I said I would do a very broad overview of NMR metabolomics, and I have to talk about statistical analysis a little bit. It's not my background, but as an NMR spectroscopist, you have to start becoming very well versed on what shouldn't be done with NMR metabolomics. So broadly speaking, we're looking at multivariate data sets, okay? So you can look at this as a univariate test, but there are multiple variables. So you're going to be doing multiple univariate tests. You could take a single peak and do a univariate test. If you have two groups, that's some sort of t-test. If you've got more than two groups, it's typically a one-way ANOVA if you want to treat these things as equals. You need to think about the number of tests that you're going to have to do. And if you're doing a univariate test on multivariate data, you must adjust for the amount of tests that you are doing, or you're going to compound that error. Remember, most p-values 0.05, 1 in 20 are accepted false positives. So these are the pitfalls that are actually common in the scientific literature on metabolomics, which is why I'm sort of key papers are very valuable, I think, to make sure people adopt best practice, not some practice in metabolomics. I'm not going to dwell on this, but I would like to point out that there are also assumptions with every hypothesis test that is done. Normal distribution. So have you got a nice, well-defined Gaussian distribution? Equal variance between populations. That's one that actually doesn't seem to be well reported in the literature. And even if you have paired samples, so actually can you have a patient before and after a treatment would be a paired sample rather than patients with and without a treatment, separate individuals. All three of those allow you to access different hypothesis tests. And there's a rather out-of-date study here, but hopefully there might be more ideas coming from the rest of the speakers. So I just wanted to highlight this slide. There's a lot of choice, even on a simple univariate test. And then we go to multivariate models, which I know the other speakers are going to talk about more, so I'm not going to worry too much about going into this, but I wanted to highlight a challenge for those of you who aren't doing metabolomics and see these two plots and go, they're the same. Because this is actually an output from a very standard statistical package, I would say, server called MetaboAnalyst. It's a great way to upload data and get results out. But you need to know what you're looking at. Even if you never do a metabolomics study, if you get a review of a paper on metabolomics, you need to know that these two plots are very different from each other. So the PCA, the principal component analysis, is an unsupervised analysis. Each spot represents a spectrum, represents a sample, represents a data point. And each of those spots is basically closer together if they're very similar, and further apart if they're varied from each other. There's no bias. There's absolutely no reason why these colors are applied other than at the end we said, okay, now color these red and these green. The opposite is true for the plot adjacent to it. So this plot here is a partial least squares discriminant analysis, and as the name suggests, it discriminates, it biases. You tell it in advance what your groupings are, so what's red and what's green, and it will try and force those samples apart. Now, how it does that depends on how ruthless you are with it, and these papers at the bottom here will talk a lot about how to handle a partially squared discriminant analysis correctly. They need to be validated. You need to actually say that this is a valid result. So this is the same data, so you can see the value of the PLSDA actually helps separate things where maybe they're closer together than you thought. But also the degrees of freedom, the number of components that you use for your discriminant analysis needs to be such that you don't overfit. So you can see this is 1 degree of freedom, you've got noughts and crosses, and you might have underfit that model. You may build a more complicated model with more components, and you start to separate the noughts from crosses very well. You could always ask your PLSDA, and some do, to just force everything apart. So you can add as many degrees of freedom as you need to force every nought from every cross. But of course, the challenge is, can you actually do that with a new set of data? If you bring new sets of data, will the noughts and crosses be in the same place? The answer is no. This is an example of overfitting. Again, this is going to be covered more later, but it's such an important point because PLSDA abuse happens in metabolomics all the time. It is a useful tool, We use it, but you do need to know how to use it well, and you need to know how to interpret it. So looking for metrics, this is one example of a metric. This is a simple PLSDA from the Metabolomics online server. It will give you a Q-squared or a predictive sum of squares, which basically tells you that the ability for these samples to be laid out, cross-validated and put into the right group is okay. Now, that doesn't mean that another set of data will be the same. That's a different validation that also should be applied. I did scramble the labels on these samples. These are the same samples. And now blue and orange don't mean anything. So these are no longer clinical groups, just to show you that a PLSDA will force anything apart. You just ask it. Okay, so these are the first two components. The challenge is, even with a reasonable separation on 5 components, you might actually think, okay, well, this score's pretty good. But the actual predictive power has disappeared. So you really need to know the devil in the detail when you're looking at the PLSDA. The PCA, the peaks remain in the same place. There's just the colours that have changed. Sorry, the samples remain in the same place. So that was my whistle-stop tour of how NMR Metabolomics pipelines progress. And I'm just going to check the time before I get into trouble. I would like to talk now about a little bit more in the NMR Metabolomics part. So we do a NOSI presat, a CPMG presat, or an LED as our typical proteinous material suite of spectra. This is all one-dimensional NMR. So why we use a NOSI is really, it's a cheat. It's not doing anything that a NOSI normally is used for. It's just a really good way of cycling out the water. And they've actually found that you can do the 2D NOSI with one increment and a few tweaks to presat filters to actually get you a very well suppressed water with a lot of the metabolites around the water and the metabolites that overall not being able to perturb. So it's a traditional one. I'm sure there are better water suppression out there now, but we don't throw anything away, especially when we do statistical analysis and compare things together. The presat and the NOSI presat's here to stay, I would say. We also can for samples with a large molecules around the small molecules, we can get rid of that albumin, that protein background altogether by performing a 1D CPMG presat. So that will obviously get rid of anything with the short T2. And in the LED, the opposite is true. So that's a longitudinal eddy current delay. So it's a diffusion experiment. So essentially you apply a gradient, you reverse that gradient, the small molecules will have wandered off, and those things that are not diffusing very rapidly will be able to be encoded, decoded, and therefore you actually are left with just the large molecules or the slowly diffusing molecules, and the small molecules have all attenuated. So these are my attempts to explain what's happening there. Basically, what it looks like is here is a serum sample we collected in Liverpool. The NOSI presat is a mixture of large and small molecules. You've got albumins, you've got small molecule metabolites. The CPMG presat gives you that lovely flat baseline, which is great for quantification. And the LED is the reverse. You're just looking at the large components that are left behind, the albumins, the decorations on your low density lipoproteins. And they're the 3 spectra that we tend to run for clinical samples. I say tend to, if you're doing a metabolite extraction, you tend to precipitate out the proteins, and therefore the question of getting the large molecules away from the small goes away, and you've just got small molecules left. So a biofluid NMR spectrum, this paper is from the Finnish group who actually went on to form Nightingale Healthcare. They're a large metabolomics provider who use mainly NMR to provide metabolomics services to researchers. And this is just really to illustrate the variance, the wide amount of metabolites that you can see in a serum sample. This is a CPMG serum sample, so you can see there is a flat baseline. You still get the mobile lipids the decorations on the low density and the high density lipoproteins. What we do to handle the data is another challenging aspect, and this is the one that we've been really talking to CCPN a lot about, is how we actually go from the spectrum to that matrix of numbers. So there's a few software that actually will do incremental binning. You can just chop up your spectra, and basically that's quite good for just taking every data point and looking to see, are they the same, are they different? You can apply the statistical tests, you could do a fingerprint, but you wouldn't actually know what metabolites are giving rise to what. Variable binning is a little bit more advanced. That way you can actually start to assign values to each peak group. So you can actually say, okay, this is metabolite A, this is a mixture of B, C, D, and E. And that allows you to obviously do some statistical analysis, but also infer what metabolites are leading to the changes you hopefully are seeing in your statistical analysis. Spectral deconvolution is obviously the big one. That is one that would be really valuable to apply. You can do this with proprietary software such as Canonics. This is all geared up to serum, plasma, and urine. So the metabolite library is provided by the software, and you can fit all of the peaks together in your biological sample and export a single value for each metabolite. There's also way fitting programs such as Batman. This was written in R. I think this was from Tim Eccles down in Imperial. And, you know, again, it does the same thing, but there's a high pain threshold to get it working well. I think that might be the fairest way to say it. So I haven't seen it used much outside of the groups that develop it. Essentially, what we're doing in 1D NMR is pattern recognition. So you take a whole load of standards that you've run and basically you match them with your metabolite extract here. And you build up all the metabolites that you can find that match all of the peaks in your spectra. And that is how you annotate your metabolite profile. So basically, you overlay multiple standards and you adjust the intensities to match. I say annotate and not assign because there's a bit of language that the metabolomics community have developed, annotation and identification. And this was really from the MS community because there's a lot of MS providers that actually give you a sort of predicted, oh, master charge, it must be this molecule, or this is your profile, it must be this molecule. Lots of predictive tools. We're not quite so lucky anymore, I'd say, but actually there was a lot in the literature of metabolite X is changing, metabolite Y is changing, and they had no proof of why that was or what that metabolite was. Basically, they had something matching from their software, their third-party software, and they just said, oh, well, it's that. And there's a lot of very hard-working MS groups who actually run authentic standards, run everything fragmented in the same manner, and actually cross-reference with multiple pieces of evidence that this is indeed, this signal arises from that metabolite. But it's true for NMR as well, okay? We can match an external library and say, yeah, that looks like that metabolite. But you, without actually having run an authentic standard that you've run on the same instrumentation and you've actually matched by two orthogonal pieces of evidence, you are only working with an annotation. So you need to meet these two criteria to get to the standard of identification. Now, for MS, it's quite obvious, it's retention time on the column that they're using, so it's LC or GC column, and master charge ratio. And they're usually the two orthogonal pieces of evidence they want to be justified. NMR is not quite as easy as level 1 identification or level 2 annotation, because if you've got a complex metabolite, you've got J coupling and you've got chemical shift. Now, you could argue that those two pieces of evidence are orthogonal, but it's not really the principle of the idea. So really, and also not all metabolites will have J couplings. So really what we're looking for is maybe two different sources of chemical shift, like a proton and a carbon, or, you know, even actually an NMR and MS data set together. So again, reporting checklists and metabolite standard initiative, seminal piece of work there for you to look at. So we're looking at in-house verification. I would say CCPN is very good at actually allowing you to look at the 2D as well as the 1D together. That's quite a rare treat in NMR Metabolomics. A lot of the software is really geared to one dimension and that's it. And basically you can confirm the metabolites you've seen there quite readily with a range of spectra. The J result here is that pseudo 2D where you've got in one axis the proton chemical shift and in the orthogonal axis the J coupling, which is where you can come to this two orthogonal pieces of information. So how am I doing for time?
10 minutes.
10 minutes, all right, okay. So this is where I talk to you about my favorite topic, which is lipids in NMR. And there's a lot of enthusiasm for lipids. It's a big biological group that is actually very important in terms of clinical outcomes, diseases, and basic biological functions. But lipids means different things to different people. I really quite like this paper again. It's from the Finnish group who went on to form Nightingale Health. They used to run a LED or a diffusion experiment for the serum, CPMG or a low molecular weight spectrum for their serum. And then they'd go on and they'd freeze dry the serum down and resuspend it in deuterated chloroform or deuterated methanol, depending on their method. And then you'd actually get a lot of information on the lipid head groups within the sample, along with a whole mess of information on the hydrocarbon chains. The group in Imperial have also actually looked and spent a lot of time investigating the density lipoproteins, and these are molecules of interest in intact serum. So again, this is an LED spectrum, and you can separate the very low density lipoproteins from the low density lipoproteins, from the high density lipoproteins, and even the intermediate density lipoproteins via this method. Basically, this requires a little bit of deconvolution and some very proprietary algorithms, I would say. So we're not quite there as an open source tool to actually analyze those yet. But this is one of Bruker offer a version of the algorithm with their metabolomics package, and this is really where the interest becomes quite prevalent in the metabolomics of very large molecules, which it's questionable whether you consider them metabolites. The group that actually Gunther Ulrich is now part of over in Germany, they've actually gone one further and started looking not just at the lipoproteins, but also the glycoproteins, and doing something like a selective NOE to actually highlight the two different glycan decorations on glyc A and glyc B. And that's really important and actually has become a marker for inflammation and actually is now the COVID test. The response to COVID infection can actually be predicted, or the severity can actually be found based on this ratio of glyc A, glyc B. So this is now another software implementation within Bruker. And it's all there under the deconvolution of signals in your standard one-dimensional spectrum. So these are all accessible for a cost or for a level of pain from the NMR spectrum. When you're thinking about lipids as small molecules, as you're thinking about structures, neighbours, and environments, okay? So we're not going to be able to tell an exact lipid identity, but we are going to actually be able to say something about its quality. Olive oil does not contain trilaurelin, but does have a triacylglyceride signature within it. So these are the kinds of things that you can actually start to unpick from lipids from all over, in nature, within food groups, within biological systems, and you can actually start looking at the isomerization, which is something that our MS colleagues would dearly love for us to get our heads around and start providing them with backup for. So we've been really looking to try and build in a small lipid head group library within CCPN based on the work of the Finnish group, and basically deconvolute those peaks. So the software that some of you have been on the workshop this morning is where I aim to put our lipid library in. Oh, a little bit more on lipid profiles examples from our clinicians in the vet school. Christine Pye actually did a master's project on cruciate ligand rupture, which is probably quite prevalent given that there might be some football happening later. It happens to dogs as well as footballers, and it can happen with and without meniscal tear. So basically you can actually see the lipid profiles within the joint are changed whether there is the presence of a meniscal tear or not. Now, it's really invaluable for surgeons who actually can't see the presence of the tear without a surgical intervention. So there's a lot to be gained from drawing lipids out of, or synovial fluid out of junk and interrogating its lipid profile. She's also now a PhD student as well as a clinical vet, and she's now looking at cats, feline aging. A cat will age in about 7 years. So a 7-year-old is a middle-aged cat, and 14-year-old is a very elderly cat. And that allows a lot of paired samples, which is something that our frailty unit in the Aintree Hospital on the humans would only dream of, because you can't have a PhD student for 40 years, we asked. They said no. So instead, we've actually been helping our vet school look at these cats aging and looking at the quality of life they have as they age. And we are actually seeing lipid abundance as well as other indicators of aging. So that's in preparation. We do try and look with our frailty in humans. So we are actually translating these with the help of Jenna, a joint PhD student of mine, that she is basically enlisting healthy younger, sadly I did not make the cut, healthy older as well as frail elderly, to actually partake in a study of neutrophil biology. So we're extracting neutrophils from the blood rather than looking at blood serum or plasma, simply because people who are frail, especially if they're attending hospital, they're not actually going to be able to be fasted. So the neutrophil is the first white blood cell response. So actually looking at a neutrophil profile gives a somewhat cleaner profile on what actually is happening as these patients or in frail patients. Like I said, Jenna's not been with us 40 years, so we can't look at the same individuals all the time. But she is seeing modest response, and that's probably down to different lifestyles from the healthy patients and the frail, as well as the neutrophil response. But actually, inflammaging is the new hot topic for those who are interested in metabolomic studies. And we're looking at metabolites that give rise to an inflammatory response and impaired cell migration in the frailer elder people. So I'm going to finish by talking about a few software options. We started in-house with something called TAME NMR. A computational biologist wrote it, a Churus, not me. He was fed up of NMR not being tamed. And we looked at 1D tools, and we built this in-house server based on the Galaxy project. That was actually superseded by a great idea, same idea, over in Bordeaux, where they made NMR prop flow. It is a lot nicer to use than our in-house software, but it doesn't save your results. So I would say I've got training on those if you wanted to try and do some 1D processing rapidly and simply. Obviously, if you want to do spectral deconvolution, there's economics. But Morgan at the top here has been working really hard on actually making something that will save your results, will work with more than one spectrum at a time, and will actually allow you to do a lot more with your data, including building a sort of reference library of 1,900 metabolites, which is something that economics could even dream of. So open access databases are the other side of the coin. You've got metabolites, BMRB, HMDB, and the Birmingham Metabolite Library. And these are all sources to get your annotation out. So I would encourage you to look at those. We're building our own lipid house library, and once that's completed with NDF biospectra and NEF lipid database, we'll make that available through metabolites. We do have a little bit of data out there in metabolites already on the lipid head groups. We've been doing zebrafish extracts into chloroform for quite a while now, and it's just coming out as an F1000 protocol with the NC3R's gateway this week. I will leave it there, because I know that there is quite a lot of more interesting talks to come. The future directions are really what I spoke about: more software, more tools, and more NMR input, you know, sensible NMR solutions to the questions that metabolomics face. I think sometimes it's thought as an easy thing to do by an NMR perspective, but I think that's probably because you haven't thought about how to do it in a more kind of complicated way, because definitely there are some speakers here who will tell you that it can be very complicated and NMR might be part of the solution. So I will leave it there. Thank you.